Welcome, ladies and gentlemen. Today we will be answering some questions from our homework. I was fortunate enough to get some questions from about 3 of you in class today, and so let's go and take a look at them. They're all on page 700. They all deal with our newfound topic, Taylor and Maclaurin series, a couple of radius of convergence questions. Let's go with number 19 first. It was the first question asked, and so the directions are to find the interval of convergence of the power series and find a familiar function that is represented by the power series on that interval. So actually, this problem is best done reversed. It might not be a bad idea to find the familiar function first and then find the interval of convergence after the fact. And so, understandably, this is really complicated looking because it doesn't seem to fall under the vein of any power series we've seen. It's not like sine x or e to the x or anything like that. But remember, all series, they are going to establish some type of growth pattern that we see, and it looks like each time we're moving to the right, it looks like we're multiplying by x each time, or some type of x, right? It's going to alternate, so I know that the negative 1 to the k plus 1 is going to play a role in this. So you could actually say it's being multiplied by x, or you could say that it's being multiplied by negative x to get to each next term. So what does that mean? Because we're multiplying by a straight up value each time to get to the next term, that makes this a geometric series. So why is that helpful? Well, that allows me to find the function, because the function of the geometric series will be the sum of the parts as we add straight up towards infinity. So with that in mind, you can call this 1 over 1 minus negative x. Now, where did I get this formula from? Well, S, remember from the infinite geometric series, was a sub 1 over 1 minus r, which, in this case, r is what we are multiplying by every single time, and that's why I did 1 minus negative x. So if I was to simplify this thing, it would be 1 over 1 plus x, and this thing would only converge if the absolute value of r was less than 1. Now, in this case, that would have to be the absolute value of x being less than 1, meaning negative 1 had to be less than x, which was less than 1. And this right here, this is your interval of convergence right here. And because it's a geometric series, we actually don't need to test out these endpoints using any other test, because with a geometric series, we actually know that the absolute value of r is less than 1, not less than or equal to 1. That would not be correct. We're not going to put that there. So we don't need to test the endpoints. We can just say the interval of convergence is from negative 1 to 1, non-inclusive. So that is it. Number 21 is done the exact same way. So let's go and take a look at it. All right, let's go and take a look at number 21 right here. So with 21, again, it looks like the r is equal to x minus 2. That's how we're advancing each time. So if I was to write a formula for this, f of x would be 1, right, a sub 1 over 1 minus r, so that would be x minus 2. So that would be our formula. And now for the interval of convergence, that would have to mean that the absolute value of x minus 2 would have to be less than 1, since the series is geometric. So that means that if I was to center this guy at 2, he'd be 1 out in each direction. So from, not negative 1, but regular 1. So it looks like my interval of convergence would be from 1 to 3. So again, with 19 and 21, I believe that the hardest part was recognizing that it's a geometric series. It's really hard, especially because we deal with so many complicated series as we move forward, that we always forget the ones that we had before. So hopefully that makes a little bit more sense. I will erase the board and come back with number 27. Alright, now we are on number 27. Now, unfortunately, this is not a geometric series. It's going to be a little more complicated than that. If we're going to find the radius and the interval of convergence on this particular series, what we want to employ is we want to start employing the ratio test for absolute convergence. So what I'm going to do is I'm going to say, all right, the limit as k goes to infinity of the absolute value, and that gets rid of the alternation, which is this negative 1 to the k. I can call them x to the k plus 1 over k plus 1 factorial times k factorial over x to the k. From here, I'll go ahead and split my terms up, and I'll make him k plus 1 times k factorial. Now, why did I do that? It's because it allows me to see the factorial pieces canceling each other out faster. And so hopefully we understand why this happened. Remember, factorial is just, something times the term before it times the term before that, and blah, blah, blah. Looks like the x to the k's are going to get out of here. The k factorials are going to get out of here. The limit as k goes to infinity of x over k plus 1. Okay, so now from here I can see why this would be confusing, because we're taking the limit as k goes to infinity, and that's it, only k. So because there's a couple of different variables here, there's an x and there's a k, x, it's not changing, and one might even consider it a constant. So if I consider the constant value of x, no matter what that value is, that constant value, as k goes to infinity, I will get 0 as my limit. Because any constant over any variable, as that variable approaches a larger and larger value, will end up becoming nothing. And as a result of that, when we do the ratio test for absolute convergence, we compare the result of our limit, in this case 0, we compare that to the number 1. And in this case, because 0 is less than 1 for all real numbers, we can say that the radius of convergence would be infinity. And then the interval of convergence would be from negative infinity to infinity. So what does this mean? Well, what it means is that whatever polynomial whatever non-polynomial function this polynomial is meant to represent, the more terms you add on top of this series, the more accurately it will represent its non-polynomial counterpart, and that will extend for all real numbers, and we'll just keep flattening out, and it'll keep getting closer and closer for every single number across the coordinate plane. I hope that makes sense. Let's move on to number 29. All right, let's go and take a look at number 29 here. Now, before we move, I think it might not be a bad idea to rewrite this a little bit. It's a little complicated looking, but this 5 is being raised to the k, and so is this x. And so what I can do is I can combine them out to make them a full blast 5x to the k over k squared. And then what I'm going to do is I'm going to go ahead and do my ratio test for absolute convergence here. So it'll be the limit as k goes to infinity of the absolute value of 5x to the k plus 1 over k plus 1 all squared times k squared over 5x to the k. And now from here, the limit as k goes to infinity, I'll go ahead and just split up my terms, so 5x to the k times 5x to the 1 over k plus 1 squared times k squared over 5x to the k. And I apologize, that should be in parentheses as well. The 5x to the k's all go away, and I think that's all that's going to go away. So the limit as k goes to infinity, it will be of 5x times k squared over k plus 1 squared. Now, if you've noticed, every time I do the ratio test for absolute convergence, what I do is I put all my non-k terms on the left side of the multiplication and all the k terms on the right side of the multiplication. That allows me to just kind of ignore this 5x, because again, just like the last problem, the x isn't going to play a role as k goes to infinity. One might consider it a constant value. So all I have to do is take the limit as k goes to infinity of k squared over k plus 1 squared. Now, before we jump the gun here and say, oh yeah, it's definitely going to 0 because the k plus 1 on bottom is larger, remember, limits that go to infinity depend on dominant terms. So this is technically k squared plus 2k plus 1. My dominant terms are k squared over k squared, so as k goes to infinity, this whole thing becomes the number 1. Leaving me only with 5x. And then the result of that limit, I will then compare him to 1, and I want him to be less than 1 to find the interval of convergence. So from here, what I'm going to do is I'm going to go ahead and pop out that 5, because absolute value of a constant is a constant, which means the absolute value of x has to be less than 1/5, so my radius of convergence will be 1/5 in either direction, and because this x is centered at 0, I know that my interval of convergence will be from negative 1/5. I'll move him actually. The interval of convergence will be from negative 1/5 to 1/5. Now, I'm actually not out of the woods yet because I now need to determine what types of brackets I'm going to put around that negative 1/5 and that 1/5. I'm not sure which one it's going to be. And if I'm going to find out what types of brackets those are going to be, I want to know if we're going to be converging exactly at those places. So how do I do that? Well, what I'm going to do is I'm going to, first off, eliminate my ratio of absolute convergence test. And what I'm going to do is I'm going to go ahead and use this version of the summation. And I'm going to let x literally become the negative 1/5 and the 1/5, the endpoints of my interval of convergence. And I will find out whether or not the series actually converges there or not. So, at x equals negative 1/5, well, what that gives me is it gives me the sum from k equals 1 to infinity of 5 times negative 1/5, sorry, that's a nasty 5, to the k over k squared. And now from here you can go ahead and cancel him out, and you're going to get the summation from k equals 1 to infinity of, looks like, negative 1 to the k over k squared. Couple of different things you could do here. You could use the alternating series test if you wanted to, or you could compare him to a p-series. It's completely up to you as to which one you want to use. I would probably just use the alternating series test because it's alternating. So I would say a sub k is alternating, a sub k is decreasing in absolute value, and then the limit as k goes to infinity of a sub k is equal to 0, and therefore the sum from k equals 1 to infinity of negative 1 to the k over k squared converges by alternating series test. And what that gives me is it gives me the ability to do this. Boom. That hard bracket right there. If I haven't mentioned it before, that is why we learned all those convergence tests. It really was the culmination of whether or not you were able to put a hard or a soft bracket on your radius of convergence. So in case you were wondering why all those tests were necessary, it is so that we could make a determination of bracket. So, yeah. Good stuff. K equals 1 to infinity of, looks like, 5 times 1/5 to the k over k squared. Goodbye. So then you could say sum from k equals 1 to infinity of 1 to the k, or just 1, rather, over x squared, or rather k squared. And then you could say converges by p-series. Whoops, not that. Because p is greater than 1. So, with both sides equally convergent, that gives you the power to throw down a couple of hard brackets, and then you can call this problem a day. Your radius of convergence is 1/5 long, and your interval of convergence is inclusive of negative 1/5 to 1/5. Alright, let's go ahead and take a look at the last problem, number 35. Alright, let's take a look at number 35 here. We are being asked once again to find the radius and interval of convergence of this particular series. So again, it really boils down to one main weapon. It's the ratio test for absolute convergence. And I will see how this thing pans out. So it'll be x to the 2k plus 1 plus 1 over 2k plus 1 plus 1 factorial times 2k plus 1 factorial over x to the 2k plus 1. So standard operating procedure on the algebraic manipulation here. This is going to be a 2k plus 2 plus 3, so it'll be a plus 3 here. So I've got the limit as k goes to infinity. Whoa, that should be an infinity of x to the 2k plus 3 over 2k plus 3 factorial times 2k plus 1 factorial over x to the 2k plus 1. So it seems like it's the same thing. We're going to go ahead and just split up our terms here. And again, you don't have to show this part. I like to, just so people can see what I'm thinking here. X cubed over 2k plus 3, 2k plus 2, 2k plus 1 factorial, times 2k plus 1 factorial over x to the 2k times x. So all the 2k plus 1 factorials are going to go away. You get these guys to go away. These guys are going to kind of go away. And you end up with the limit as k goes to infinity of x squared over 2k plus 3 and 2k plus 2. Now, if you're sensing that I'm feeling a little more relieved on this problem, it's because I am. And I think it's because we can reasonably predict that if where this thing is going to go. And the lazy calc student in you should be very happy about this, because this is going to go to 0, which makes your radius of convergence infinity, and your interval of convergence negative infinity to infinity. Okay, I think that just about wraps it up for the questions. Feel free to leave any additional questions about these questions in the comments section. If I haven't made something clear, please let me know so that way we can clarify it. I hope you are all staying safe and staying indoors. And stay tuned. We will have more videos for you guys as we continue to prepare for the AP exam. And I will see you all next time.